there. All right, I had a couple of questions about number 32 on the test. Number 32, I gave enough information in class. I mean, this is a take-home exam, so I expect you to have to look things up and dig through the stuff. But this one, you don't need, for example, you don't need molarity. Molarity is a different concept. You need to know what the percentage is, which we talked about percentages before. You know, you need to know about isotopes, which we talked about isotopes before. You need some other stuff, you know. The other stuff was in class, in the lectures. Also, you probably can find it in the book or online as well, some additional information. So I didn't want to make it too easy, you know. So I gave you the masses of O16, H2, etc. And so I didn't put them in this problem because I expect you to look those up. And so to make a take-home test, as otherwise, if the take-home test is going to be the same as an in-class test, then I have to do it differently. You know, then I have to restrict this. It's going to be closed book, that kind of thing. But it's hard to control that. So this is just open book, and you can find that information. Actually, I brought it up in the. It's actually look at the PowerPoints. This is a hint. Look at the PowerPoints. You know, and start looking for information. And it's just a dimensional analysis problem. Dimensional analysis problem, you just start and then you just try to see. There aren't that many paths you can go down. You know, a lot of people will leave this type of problem blank because, you know, it's like being frozen in the jungle. You know, each path is, you know, mysterious or, you know, somewhat scary to go down a certain path. And so you just freeze up and don't want to even try. But what you want to do is you just want to go through it. There aren't that many choices once you start putting pencil on paper and then trying to cancel out the units. And so just work on it. You could turn it in later today, or yeah, that's right. All right, is it due? I said it's due Monday, so yeah, if you can turn it in today, you know, Monday, we can move on. So yeah, that's okay. 11:59 p.m. is okay, or midnight, whatever. If you're still having issues, you know, just get it in by tomorrow morning. That's okay. You can get it in by tomorrow morning. That's fine. Tomorrow morning, before, let's say 9. Wait, I'm not sure if I'm going to print these ones out.
Professor,
we only have 2 weeks left, actually.
Someone on Piazza is asking for the Zoom link.
I'm sorry?
The Zoom link isn't on Piazza.
Oh, Zoom link on Piazza. Shoot. All right. I need to do that.
Thank you.
Okay. Sorry about that. The people are probably waiting to try to invite participants. All right, yeah, since I forgot to post a Zoom link there, let me give it a few minutes to let everybody log in, and then I'll just talk about it one more time. So you're going to have to figure it out. I can't tell you step by step how to do this. I mean, it's a take-home exam. There's enough information to solve it. The thing is, you got to remember the strategy. This is a hint. The strategy is you're given something and you try to cancel it out. Now, how many choices? There aren't an infinite number of choices. If there are an infinite number of choices, then obviously you're going to need a lot more assistance. But there are a minimum number of choices, and even if you pick the wrong one, it's no big deal. If you pick the wrong one, what you do is you go back and then try a different one, and so you work on it. You know, all the information, like I said, is not in the problem, but it was given in the class or the PowerPoints, or you can find it in the book. You know, or if you get desperate, you could look online for the information, you know, but the information was given in class. And so enough information to solve this. So give it a try. Let's see, you know, there's partial credit too. If you don't successfully get an answer, you should show as much work as possible. That way you can get more partial credit. You know, worst thing is just to leave it blank and do nothing. You know, if you leave it blank, you're going to get 0 points. At least try to recover some points, you know, by making a start to it. That's the best. All right, so that's number 32. Again, it's a take-home exam. If you guys want the regular test, then I have to do it totally different. And so take-home exam has to be a little bit of work, you know. I can't put a little bit of work in that you have to look up some information, but it should all be there. Okay. All right, let's move on here. Okay, let's take a look at some more. I wanted, since we have 2 weeks left, pretty much, looking at the syllabus here, I'm a little behind. So I'm still working on 12-13, it's August 3rd, but 19 is not going to take this long. So I'm going to compress 19 a little bit. And then we'll talk about 14 and 15 and 16. Probably get through 14, 15, 16, 17, 18. Yeah, 14 through 18. So a lot of chapters, but some of this stuff we covered before, like acid-base reactions. We covered those, Bronsted, pretty much. And redox, we covered redox reactions, single replacement, and the Chart method, and the skeleton redox method here. So the only thing we didn't cover is batteries. So we'll probably do something equilibrium. Let's do a survey of that. And we have some labs left, a number of labs left here. Experiment 6, well, I have the numbering mixed up because they changed the numbering. But we did experiment 6 last time. But we'll get through these labs, doing titration Thursday. And 12, we're doing something called qualitative analysis. And then experiment 13 is mostly just looking at some redox reactions. It'll just be something we'll just do in class, just observations of redox reactions. All right, so let's take a look at doing some Lewis structures here. I think we're looking at NO2 plus, N2O, NO. So let's take a look at NO2 plus first here. For organics, sometimes we just draw out the skeleton. We kind of know how the organics bond, like how carbon bonds, you know, 4 singles, you know, double, 2 singles, 2 doubles, etc. For these, what we call inorganics, the difference between an organic and an inorganic is that organics are carbon, hydrogen-based, you know, compounds. So they typically have carbon and hydrogen, and then other elements like oxygen, nitrogen, etc. inorganics are mostly the rest of the periodic table. There are some carbon-based inorganics. Should be like CO2. CO2 is considered an inorganic. Carbonate is considered an inorganic. So typically there's hydrogen in there. All right, so NO2 plus, what we do with that one is we just do our standard first we count up the valence electrons. So for NO2 plus, we have nitrogen with 5 valence electrons, 2 oxygens with 6 each, so that's 12 electrons. And then the plus 1 charge. Plus 1 charge is remove 1 electron. Did I already do this structure? Not exactly sure. This 17, that's going to be 16 total electrons. Now nitrogen we would put maybe in the center, put the oxygens on the outside here, like that. Because nitrogen is less electronegative, and we typically put the more electronegative elements on the outside unless there's no choice, like in water, the more electronegative oxygen goes in the center, but there's no choice because hydrogen does not form more than 1 bond here. And so sometimes it's just a rule. Sometimes it's violated, but if we have an option, we try to put it in the center like this. I think I already did this. And then we'll do, we fill up the valence electrons, or the octet, in other words, for the terminal atoms. But what this is 16 electrons now, 2, 4, 6, 8, 10, 12, 14, 16. But that doesn't leave nitrogen with an octet. And since nitrogen doesn't have an octet, what we'll do here is we're going to form multiple bonds. So we'll just take one, this oxygen will sacrifice here, form a double bond here. That's still not going to be enough. This oxygen will have to sacrifice here. And then we'll form another double bond. And then that should be enough. So let's try that. So each oxygen lost a lone pair here. But now nitrogen has an octet. Now when we look at the formal charges of the oxygen here, first we look at the octet, then we'll look at the formal charge. Formal charge, we count the electrons, 1, 2, 3, 4, 5, 6. 6 electrons on oxygen. Oxygen is supposed to have 6 electrons. Since oxygen came out even, we'll just say it's a 0 formal charge. It contributed 6, it got 6 out. And so, same thing with this oxygen, but this nitrogen, it contributed 5, but it got 1, 2, 3, 4. So it contributed 5, but only got 4 electrons out. That means it's got a positive charge like this, and we have a net positive charge for this. So this is the NO2 plus on that. I think I did N2O already, N2O, we did 2 different structures. Do you guys have N2O in your notes? We did a structure where we put oxygen in the center and nitrogen in the center. Yeah. No? We'll take a look at N2O. N2O is 2 nitrogens, it's 10 electrons. Each one is 5 electrons. And then 1 oxygen, which is 6 electrons. So that's, again, 16 electrons. Now we could put oxygen in the center like we had over here with water. Or we could put nitrogen in the center, like this. And then just try both. In problem solving, in general, in problem solving, oftentimes you don't know. That's why it's a problem. If you knew the answer already, then it's not much of a problem. And so in problem solving, you have to take some risks. You know, this might not give you the right answer. This might not give you the right answer, but you have to take that risk and then try it, see where you go. The same thing with dimensional analysis. You know, you might not know which way to go, but you just try it and see what happens. So we'll do the same thing that we just did with NO2, and that is just have this nitrogen contribute one pair, this nitrogen contribute one pair, and then we end up with this structure here. You know, this one looks good like NO2, you know, like this. Everybody has an octet. If you look at this nitrogen, there's 2, 4, 6, 8. You know, when we count the octet, we look at the total number surrounding. So this nitrogen has an octet. This oxygen has an octet. This nitrogen has an octet. You know, we double count the electrons. So for, you know, since they're being shared, so this nitrogen takes all these 2, 4, 6, 8. This oxygen takes the same 2, 4, 6, 8, 2, 4, 6, 8. But when we count formal charge, then we have to split them. So let's count formal charge next. So everybody has an octet, but looking at the formal charge is 2, 4. These belong entirely to nitrogen, and then half of these, there's a total of 4 electrons. So that's 6. Well, nitrogen only contributed 5 each, and it got 6 in the structure, so it's got a negative formal charge. Formal charge is circled. Yes. Oxygen ends up with, well, half of these, that's 2. Half of these, that's 2. Oxygen ends up with 4. Oxygen contributed 6. So it came out too short, so that's +2. And this nitrogen is the same as that, so it's going to have -1. And so one thing to notice about formal charge is, you know, everybody pooled their money in. This is like, you know, Californians pay a lot of federal tax, you know, so they pay tax to the U.S. government, federal government, but how much of that do they get in return? So if you pay $1 in federal tax, how much of that money goes back to California, let's say? You know, is it half of it or what? It's best if you contribute $1, then that dollar is being used for, you know, used in California for essential, you know, government functions. And so if you contribute $1, that dollar ends up in California, but that's not how it works. How it works is, you know, Californians contributed $1, and then that dollar is split up amongst other states. So some states will get more because they just don't have enough revenue, and other states will get less. So California will get less. Well, this is like the oxygen here. You know, oxygen would be like California. You know, they'll contribute 6 electrons, but only get 4 electrons back in this structure. Well, what we try to do is we try to minimize formal charges, because the more formal charges you have and the higher they are, you know, the less equitable, you know, the distribution of electron. Here we can't avoid it because this is a cation anyway, we're missing an electron. Here, you know, here we'll try to, well, this is not, you know, 2 nitrogens taking electrons from oxygen is not, you know, oxygen's more electronegative. So and then 2, you know, oxygen losing 2, it's harder to lose 2 versus 1. And so the formal charges here throw up a red flag. The red flag is these are kind of high. So let's take a look at this structure over here. You know, sometimes formal charges can't be avoided, like here. But if they can't be avoided, we'll try to minimize them, you know. We could try to minimize this one. There's an easy way to minimize this one. And one easy way of minimizing, actually, let me go back to this structure here, is to try to do it one more time. Rather than having this as a lone pair, we'll try to share these. If we try to share these, then what we're going to see is this happen, where we can get rid of the formal charge. Like this. Now, And do you see, if we look at the formal charge here, nitrogen is going to have 1, 2, 3, 4, 5, half of these. And so that's going to get 0 formal charge here. And oxygen is going to end up with 1, 2, 3, 4, 5, 6, 0. So oxygen contributed 6, it got back 6. So now it's happy. Nitrogen contributed 5, it gets back 5. But what is the problem with this structure? This structure is bad. Bad structure. And so why is this a bad structure? Does anybody see it right off? Are you guys working on the test, or? Yeah, I kind of figured. It's not triple bonds. Triple bonds are okay. There's another reason why it's bad. Does anybody see the other reason why it's bad? It's related to the triple bonds. Yeah, it's pretty much, the zeros are good. The bad part is this. This is why it's bad. Nitrogen's okay. You know, nitrogen's okay because when we look at nitrogen, nitrogen still has an octet. So that's 2, 4, 6, 8. And so both nitrogens are happy. The problem has to do with oxygen. When we look at oxygen and we look at the total number of electrons around oxygen, it's 2, 4, 6, 8, 10, 12. That's 12 electrons. 12 electrons is much, much greater than an octet. An octet is 8 electrons. So sometimes we can have, this is called an expanded octet. The problem is this: carbon, nitrogen, oxygen, fluorine cannot have an expanded octet. However, you know, if you go below that, phosphorus, sulfur, chlorine, and below, etc., sometimes can have an expanded octet. And so an expanded octet means just more than 8 electrons. So oxygen will have more than 8 electrons total surrounding it. And so this structure won't work, whereas this one is good. This is, we have an octet here. Now the octet rule is the most important. And so here we tried to lower the formal charge more by donating electron density from nitrogen to oxygen here by making a lone pair and a bonding pair, but it's not going to work because we can't expand that octet. So we're stuck with this structure. This is it. So we got this structure versus, well, let's put nitrogen in the center and see what we can get here. And so we could try the same thing here and just form two double bonds like that. And so if we do two double bonds, then we'll get this. Now let's look at the formal charges here. The formal charges here, this nitrogen has 1, 2, everybody has an octet. First, we gotta look at the octet. So you draw a circle around this nitrogen, encompassing all the electrons. It's 2, 4, 6, 8. The same thing around this nitrogen, it's 2, 4, 6, 8. And then this oxygen, it's 2, 4, 6, 8. So the total number of electrons surrounding each atom is an octet. And so the octet rule has been satisfied. And then we look at the formal charge. The formal charge is going to be 2, 4, and then half the bonding. So that's 6. So nitrogen contributed 5. It ends up with 6. That means it gets a negative charge. This nitrogen contributed 5, but it ends up with 1, 2, 3, 4, half of those. So contributed 5 ends up with 4, gets a positive charge. And this oxygen contributed 6, but it ends up with 6, 2, 4, 6 here, half of those. So it's 0. So we have this. Okay, that's one option. Another option works like this. Another option is to, rather than make two double bonds, we could try to do this. And so alternatively, we could have this lone pair again create a bond in this one. And so this is option 2 here. This is going to be option 1 here. So if we go to option 2, then what we end up with is a single bond here, then the nitrogen, and then a triple bond here, like that. Is this better or worse than this structure? Well, let's take a look at the octet rule. The octet rule is still fine. This nitrogen has a total number of 8 surrounding it. This nitrogen has a total number of 8 surrounding it, and this oxygen has a total number of 8. So the octet rule is fine. Let's take a look at the formal charges. So this was going to have 2, 4, 6 that belong totally to it, and then half of these, which is 1. So this gets 7. Nitrogen contributed 5 electrons, and it got 7 back. And so this is -2. It's got 2 extra negative charges, 2 extra electrons. This nitrogen contributed 5, and it got back 1, 2, 3, 4, half of bonds. So that's 4. And so that's plus. And so it came out 1 short. Okay, this oxygen contributed 6 to the pool of electrons, but it got back 1, 2, 3, 4, 5. So it ends up with a plus. So which structure out of these 3 is the best so far? Is it this one, or this one, or this one? Which one do you think? This one? Well, the first, actually, so far it looks like this one. And the reason I say that is because the formal charges, I have a +2 here and a -2. These are big magnitude formal charges, And what we try to do is we try to minimize them. We try to get formal charges to 0. That's the best. And so we end up with this structure. And so this one's not as good, but there's one more choice we could make. And so this is going to be option number 3. So in number 3, what we're going to do is we're going to make a triple bond between the nitrogens here. and see what that results in. So that'll be the third structure. I'll just draw right down here. And then leave a single bond on the oxygen. Okay, again, everybody has an octet. So this nitrogen has an octet, this nitrogen has an octet, and this oxygen has an octet. Let's look at the formal charges here. This nitrogen has 1, 2, and then half of these. 1, 2, 3. So it's 2 and 3 is 5. It contributed 5 to the pool of electrons, and it got 5 out in the structure. So it's a 0. It just broke even. This nitrogen, 1, 2, 3, 4. It contributed 5. It came out short 1 electron. So that's plus. This oxygen contributed 6, and it ends up with 2, 4, 6, 7. And so it gets a negative charge here. All right. So between this structure here and this structure, one thing to notice is that both of these structures have the same magnitude. It's +1 and -1, +1 and -1. The only difference between these two structures is where the negative charge, who got the extra electron. In the top structure here, the nitrogen gets the extra electron. In the bottom structure here, the oxygen gets the extra electron. So which one's better? Oxygen having the extra electron or nitrogen having the extra electron? Which one do you think is better? Which one wants an electron more, oxygen or nitrogen? Or which one's more electronegative, oxygen or nitrogen? Okay, oxygen. Well, what were the 3 most electronegative elements on the periodic table? Or which one is the most electronegative element on the periodic table? You know, I talked about the marathon. You know, like this class is like a marathon. This class is more like a sprint, but already we're seeing, you know, we're seeing some attrition here. It's situation is, like I said, you know, you don't want to cram everything for the final, and so you need to have recall, and the way to get the recall is you know, go through the material daily so that you can recall it quickly. I know because of the unusual circumstances, obviously, you know, this being take-home exam, so some people probably have no sense of urgency or no sense of trying to memorize anything. I realize that, but you know, those people, you know, you have to worry because you know, this is a much longer marathon. This marathon goes through, you know, your upper division classes, and although for chemistry, you know, it depends on your major as well. You know, but this goes for all classes and all majors. Is that even though, yeah, the circumstances are severe because of the, you know, lockdowns and COVID-19 and everything, but there are people who are still sprinting on this marathon, you know, and they're getting farther and farther ahead. And at UCs, a lot of these classes are set on a curve, and you have to be aware of that. You don't want to fall too far behind. And so, yeah, obviously this class is take-home exams and that kind of stuff. It's not too I mean, it's stressful, but not like in class exams. But don't get into a false sense of security because there are definitely people who are on it and who are sprinting hard and who are going to set the curve. You know, and when I was at UCLA, it was a lot of people called them the dreaded pre-med students. You know, there's a, you know, nothing against pre-med. Pre-med are very, you know, I never had it, but I heard it all the time. You know, they're ruining the curve. You know, these pre-med students, and they're sprinting right along. And so be aware of that. You don't want to fall too far behind in this. And now's just the beginning. You know, as you progress, you know, as you progress, a lot more people fall. And one thing I was very surprised at was the dropout rate at UCLA. The dropout rate's pretty high. And, you know, a lot of those people didn't have to drop out. They just fell too far behind, or, you know, they just thought it wasn't worth it, or, you know, there are other reasons, you know, but, or change major. You know, another popular thing was to change major. But now you have a good opportunity. You're right at the beginning, you know, everybody's kind of close together. And so work on memorizing. I mean, a certain base amount of knowledge. Oxygen is it. You know, oxygen has a higher electronegativity. So we have a negative charge on nitrogen versus oxygen. We'd prefer it on oxygen. This structure, too high formal charges. You know, this structure, a violation of the octet rule. Carbon, nitrogen, second period elements cannot violate the octet. Third period and beyond can. And so this structure, too high of formal charges. Okay, these structures, octet's good, formal charges are as minimized as we're going to get it. We can't get them any lower than this without making another bond. If we make another bond here, then nitrogen is going to have too much. Like, so for example, we could get rid of the octet here. One way to get rid of the octet is just to have nitrogen donate some of that excess electron density. In other words, donate an electron to this nitrogen, which came out short. So this nitrogen came out ahead, this nitrogen came out short. And so we end up with a structure like this. And so this structure you might think is good because everybody ends up with a zero formal charge. But when you look at this nitrogen, it's impossible. It's impossible because this nitrogen cannot have more than an octet. You know, and even though this nitrogen is a great formal charge, it's got 2, 4, 6, 8, 10 electrons. 10 electrons is greater than an octet. And again, second period does not violate the octet, and therefore this structure is no good here. And so we can get rid of the formal charge by making more bonds, but if it violates the octet rule, then we're stuck. And so between these two structures, oxygen's more electronegative. It's closer to fluorine. Fluorine's the most electronegative, and nitrogen's up there. And so picking the best structure would be this one. Now the difference in electronegative, this is Chem 1A. In Chem 1A, the difference in electronegativity is not so huge. It's a 3,5 versus a 3,0. And so, so we still consider this one a little bit, you know, this is like 20%, this is like 80%. And so this is the best structure. This structure is okay, but not as good as this one. And so this is the one we'll go with here. A nitrogen triple bond nitrogen, single bond oxygen, formal charges like this. We could try to get rid of the formal charge here. That is, if we try to get rid of the formal charge here, we'd end up with a bad structure as well, because if we try to get rid of the formal charge by donating a lone pair here from oxygen, oxygen came out ahead by 1 electron. So if it donates here, it'll give an electron back to nitrogen. So we could try that. But the problem with this structure is we end up again with too many electrons around nitrogen. And so the formal charges are really good. everybody got what they contributed. And so it was very fair, even distribution of electrons. Unfortunately, nitrogen can't expand its octet, and so the same thing here. Too many bonds around nitrogen. And, therefore, this structure is not going to be feasible. This is the problem here. 2, 4, 6, 8, 10. 10 electrons, which is greater than an octet. And so this structure has to be eliminated. And so after a lot of work, this is a hard problem. I don't know why they put it in number 17. This should be in the challenge section. It should be in the challenge section. Is there too many options here? And it's not an easy one to do. All right, what is the shape of this? The shape of this is, linear. So we have two groups, actually. Two groups, a triple bond group and a single bond group. And so when we have two groups, then the furthest apart they can get from each other is in a linear configuration. And that's what we have here. Make some room. So the EPG, even though the one's a triple bond, the other's a single bond, we still consider two groups because we can't split the triple bond into three separate groups. Those are three groups, the three bonds that are together as one group. And so the EPG is going to be linear. Linear, it sets the angle at 180 degrees. And so the MG, molecular geometry, is going to be linear, the geometry of the bonded atoms. We got nitrogen and nitrogen. And the angle here is going to be 180 degrees. NO2 is the same, has two double bonds. And so the two double bonds is going to be linear. And the bonded atoms are in the same arrangement as the group of electrons. Therefore, it's linear in 180. NO plus, all two atom diatomics are linear. And so it doesn't matter. But let's go ahead and draw the Lewis structure for NO plus next. So NO, well, nitrogen contributes 5 electrons, oxygen contributes 6 electrons, and then there's a charge +1, which means we have to remove an electron. Who do we remove it from? Well, we don't know yet because we haven't done the structure. And so this is going to give us a total of 10 electrons. And so we'll just do nitrogen and oxygen. Now, I've used up 2 electrons in the bond here. I have 8 electrons left over. So who should get them first, nitrogen or oxygen? Oxygen should get them first because oxygen is more electronegative. And so we'll complete the octet. So that gives us 2, 4, 6, 8 total we've used, and then that's 1 left over here. But well, oxygen has an octet, but nitrogen doesn't have an octet. And so that's a problem. So we got to make nitrogen have an octet. The only way to do that is to have oxygen donate some of those. And so actually we'll have to donate not just 1, but we'll have to donate 2. Otherwise we're not going to get an octet. In other words, we're going to have to make a triple bond here. That's the only way we can get an octet. If we just made a double bond, we're still going to be short of an octet. And so we could have done it in sequence, or we could just do it once as a whole here. So now everybody has an octet. Now this is going to be a funny, very funny structure in the sense of the formal charges. Now look at nitrogen's formal charge. 1, 2, and then half of these 3. That's going to be a total of 3, 4, 5. 5 electrons. Nitrogen contributed 5 electrons. It got 5 electrons back, so it gives us 0 formal charge. Usually we don't write zeros here. Oxygen, it contributed 6. How many did it end up in the structure? 1, 2, 3, 4, 5. It only ends up with 5. And so oxygen is going to get a positive formal charge. That positive formal charge is going to make the ion here positive. Now, normally, if it comes to nitrogen versus oxygen, oxygen is more electronegative. But in this case, nitrogen is going to win because it needs the octet. The octet rule is going to trump formal charge in this case. And so what that means is that oxygen is going to end up losing in order for nitrogen to gain the octet. And so this is kind of a weird ion because oxygen has a positive charge, which is, well, it's not totally unusual because in hydronium, you know, oxygen likes to form 2 bonds, but here it forms 3 bonds, like here, but it has a positive charge. So here's an oxygen with forming 3 single bonds. Here's an oxygen forming a triple bond, essentially 3 bonds. Both of these have a positive charge. When oxygen is neutral, it likes to form 2 bonds. When oxygen has a negative charge, it likes to form 1 bond. And so this is going to be linear. All two atom molecules are going to be linear, or ions are going to be linear, 180. Okay, here's some other structures, like hydroxide. Here in the hydroxide, oxygen forms 1 bond. Well, when oxygen forms 1 single bond like that, it has a negative charge. This whole thing is going to be a negative ion. Here, when water, oxygen forms 2 bonds, it's neutral, there's no formal charge. This is going to be linear. Water we already did, that's bent at 109.5 ideal, 105 distorted. Methanol, we did something similar to methanol already. Have a lone pair coming out and then a lone pair going in, like that. So, you know, this is tetrahedral around carbon here, 109.5, and this is around the oxygen is bent, you know, it's tetrahedral EPG, but a bent molecular geometry. The ideal carbon-oxygen H angle here, the COH angle ideal, actually, let's go ahead and do that. This is EPG, is tetrahedral. But the MG is bent at 109 degrees. And so the COH angle ideal is 109.5 degrees ideal. However, we expected about 105, just we estimated at 105 because of the 2 lone pairs. 1 lone pair compresses this angle by 2, so it goes from 109 to 107. And then 2 lone pairs will compress another 2 degrees to make it about 105. Now this carbon over here, this is just going to be EPG tetrahedral. There's an abbreviation for tetrahedral, it's T sub D. Let me start using that. And the MG is going to be the same tetrahedral, and the angles here should all be 109.5. There are no lone pairs here to tweak the angle in. Although, you know, one single bond's to hydrogen, the other's to oxygen, but we aren't going to factor in the difference in the sizes of the atoms here. Okay, these are blank. Questions 19 through 30. For each molecular ion specified, write a Lewis diagram that describes the electron pair geometry, EPG, the molecular geometry, MG, predicted by the valence shell pair, the repulsion theory, VSEPR. Also sketch the wedge dash diagram for each molecular ion in question. And so here, boron only has 3 valence electrons, and chlorine, we got 3 chlorines, each chlorine 7. So 3 times 7 is 21 electrons. That is going to give us a total of 24 electrons. Now, we'll put boron in the center because boron is not very electronegative, and then throw the chlorines on there. And then we'll complete the octets to the chlorines first. So we'll need additional 6 electrons to each chlorine. Now, how many is that there? That's going to be 2, 4, 6, 8. 8 times 3 is 24. So we've used up all 24 electrons, but boron is short of an octet. Now, we could make a double bond here to give boron an octet. And so pick one of the chlorines. Let's pick this right one and make a double bond here, like this. So we end up with a structure like this. Now everybody has an octet. And so the octet rule is good here. But let's look at the formal charges here. Now the formal charge on these chlorines, 2, 4, 6, 7, 2, 4, 6, 7 are 0. This chlorine is 2, 4, 5, 6. So it contributed 7 electrons. It got 6 out of the structure. It's lost 1. And this boron is going to be 1, 2, 3, 4. It contributed 3, so it's going to count minus. Now, I mentioned that that when it comes to octet versus formal charge, the octet wins, except for boron. And so the situation here is the boron is going to have less than an octet. The reason is boron's not electronegative enough to take an electron off chlorine. Chlorine's a powerful oxidizer. So what we end up with is this. Boron is not electronegative enough. Electronegativity is how much it can pull the electron. It doesn't have enough pull. Boron is not electronegative enough to take an electron from chlorine to take. And so boron ends up with less than an octet. So this is the only one. Otherwise, we really worry about getting the octet, you know. And so we did all those structures earlier, you know, but in this case here, boron is stuck with less than an octet here. Because in this scenario, it has to take an electron from chlorine. All right, now, what if the electron comes from something else? If the electron comes from something else, then it's okay. Boron could potentially get an octet. So for example, let's take a look at this one, BF4 minus. Okay, boron has 3 valence electrons and then 4 fluorines. Each fluorine has 7. So 4 times 7 is 28 electrons. And then the -1 charge is 1 electron. And so this gives us 32 electrons. Now we'll throw a boron in the center of 4 fluorines. Fluorine does not like to form more than 1 bond. Like that. And fluorine does not form more than 1 bond. And so we'll complete the octets here. And that takes us to 32 electrons. And so now everybody has an octet. If we look at the fluorines are 1, 2, 3, 4, 5, 6, 7. So the fluorines all have 0 formal charge. They're all the same. And then boron has 1, 2, 3, 4. Boron ends up with a negative charge. But the difference between this negative charge and the previous negative charge is that it's not taking it from fluorine here. That is, none of these fluorines has lost. That is, none of them has gone positive. And so this is okay. This is okay here. So this structure is okay. And everybody has an octet. So again, the fluorine's not losing. None of these fluorines came out positive, and boron came out ahead. So then electrons coming from somewhere else. It's not taking it from a halogen. Boron does not have the electronegativity to take an electron off a halogen. All right, so looking at the structure here, let's see what the shape is going to be here. If we have three groups, a single bond, and a single bond, then the way we want to spread things out is in a trigonal planar arrangement. That is, put the three single bonds as far apart from each other as possible. And we end up with this. We could use lines to represent the lone pair as well. And so, or a lot of people do this to save time writing. Each line represents 2 electrons. Like that. Now, the EPG is going to be trigonal planar, which sets the angle at 120. The MG is going to be the same because all the atoms follow the groups of electrons. And so the MG is the same. And then the angle here, all the angles are the same at 120 degrees. There should be no distortions here. These lone pairs on the chlorine aren't going to impact boron. The lone pair would have to be on boron in order to distort the angle or change the structure. And so those have no impact. That's BCl3. Okay, let's look at BF4 minus. Now, we have 4 single bonds here, and the way to spread those out is in a tetrahedral arrangement. So if we have 4 single bonds, I want to spread them out. I'm going to get a 109.5 angle. And now those 4 single bonds are bonded to fluorines. So I'll use this to just speed it up rather than drawing 2 dots. I'll draw it like that. Fluorines. There's a negative charge here on the boron, and this whole thing is an ion, so it's got the negative charge here. But when we look at the EPG, we have 4 single bonds, we want tetrahedral. Now this is the abbreviation for tetrahedral. And so let me start using this, save time also. The MG is the same because all the bonded atoms follow the bonds there, so it's also tetrahedral. And the angle should be perfect tetrahedral angle. It's 109.5 degrees. Again, these lone pairs on the fluorine don't impact the angle on boron. You know, if there was a lone pair on boron, then there'd be distortions. But no. So those fluorine lone pairs we ignore. Distortions. Okay, let's move on. Let's look at pH 3. Phosphorus has 5 electrons like nitrogen, and then 3 hydrogens. Each hydrogen has 1 electron, so this gives us a total of 8 electrons. So phosphorus we'll throw in the center. We can't throw hydrogen in the center because hydrogen only forms one bond. That takes care of 2, 4, 6 electrons. We have 8, so we'll put in 1 more. This is good. Everybody has an octet. All the formal charges are actually 0. You know, phosphorus contributed 5, it ends up with 5. 1, 2, 3, 4, 5. Hydrogen contributed 1, it ends up at 1, each of these. And so this is a very good structure. The octet rule is satisfied and the formal charge is all 0, so that's good. Now, we have 4 groups of electrons, a lone pair and 3 single bonds. So in order to spread those out, let's put the lone pair on the top, and then 1 single bond here, and then another single bond here, and another single bond there. And so this adopts a tetrahedral orientation between the 4 groups of electrons. And so the angle here should be 109.5. Okay. And so the EPG is tetrahedral, which sets the angle. But the MG is not tetrahedral in this case. because we don't count the lone pair in the MG. The MG is just the bonded atoms. And when we look at the bonded atoms, it appears like a pyramid with a triangle base. So this is called trigonal pyramidal. And the angle here, which would be the HPH angle, is 109.5 degrees ideal. However, now this lone pair is going to impact the angle because this lone pair is directly on the central atom here. And one lone pair distorts the angle by about 2 degrees. And so we expect it to be about 107 degrees is what we expect because of the distortion due to the lone pair, due to the lone pair. That's pH 3. Let's look at H2S next. Sulfur contributes 6 electrons. Then we have 2 hydrogens, this can contribute 2 electrons to make a total of 8 electrons. And then we'll throw sulfur in the center and then throw out the hydrogens here. That takes care of 2, 4. That's 6. This is 8. Again, this is 4 groups of electrons here. 4 groups of electrons. And so I'm going to draw this a little differently. I'm going to put the hydrogen up here and the hydrogen here. This is in the same plane. Like this lone pair and this are in the same plane. I'm going to throw this lone pair sticking out of the plane. So this is the wedged lone pair here that would stick out like that. And then I'll have a dashed lone pair here that's going to stick in. And so one of the lone pairs is wedged out like this. The other lone pair is dashed in like this. This lone pair is in the plane of the paper. And so I don't draw bold and I don't draw dashed. I just draw normal like that. And so here, you know, the EPG, we have 4 groups, 2 lone pairs and 2 single bonds. So it's tetrahedral. 4 groups is tetrahedral. Now the MG here, all the formal charges are 0. This is good. Formal charges is 0 on the octet rule satisfied. The MG is going to be bent, but it's going to be bent at 109.5 ideal. But it's going to be distorted. Now one lone pair is going to distort it by 2 degrees. So one lone pair drops it down to 107. The second lone pair is going to drop it down about another 2 degrees. And so we expect about a 105 degree angle. The HSH angle should be about 105 due to the distortions. But you know, it's just about, these are guesstimates. It turns out in H2S, the angle is way off from what was. Sulfur is a big atom. In Chem 1A, you'll learn more about it, but in Chem 4, we're not going to get into it. In Chem 1A, things will be more in depth, of course. Okay, so that's H2S. That's what we expect based on Vesper stuff. Okay, let's see how they drew theirs, and let me comment on how they drew theirs. I always draw it the same way each time. So this is okay, but I'll tell you a couple of things I don't like about this. Number one, they don't have the lone pair here. I need the lone pairs in here from chlorine. Number two, I always want to draw it the same way. So you're either going to draw it like this, unless we can't, of course. If there's multiple atoms here, we might have to draw it based. But if it's just, multiple centers, just try to draw it the same way. The same thing with this, always draw it the same way. So put 2 and then 1 sticking out like this, 1 sticking in like that. Don't flip these. Your book flipped these. Sometimes they'll draw it like this, sometimes they'll draw it like that. And sometimes they'll draw it like this, and sometimes they'll draw it like that. Draw it the same way. Like this one here. This one, we put the H in the plane and this H. They aren't showing the lone pairs. Now, the lone pairs, We want to show those, even though you can't pinpoint them because of the Heisenberg uncertainty principle, but we want to show them here like that. And so I don't like the way they draw their structures. Before. We need to be a little bit more precise. All right, let's look at hypobromite here. When we look at hypobromite, bromine, actually, well, let's take it's break time. So, surprise. So we're gonna go on break. We'll go on break for 15 minutes, so 47, 52. We'll start again at 52, 12:52. Lewis structures are pretty important in chemistry, so we're falling behind, but it's falling behind because the Lewis structures is not bad. Lewis structures in Vesper. Okay. All right, so I'm going to pause the recording. Okay, thanks. Hypobromite. Bromine has 7 electrons. Oxygen has 6 electrons, and then a -1 charge, which would be 1 electron. And so that's going to give us a total of 14 electrons. And then there's only one choice, bromine bonded to oxygen here. And then we have a choice, bromine or oxygen. Oxygen should be more electronegative. You know, the higher up, fluorine's the most electronegative. So more to the right is more electronegative, and the higher up is more electronegative. So we want to go up and right. And so oxygen should get it first. 2, 4, 6, 8. And then that leaves 6 more electrons. So 2, 4, 6. So that should give us a total of, actually, did I miscount? 2, 4, 6, 8, 10, 12, 14. That gives us a total of 14 electrons here. Now let's take a look at the formal charges. So everybody has an octet. This oxygen has an octet. This oxygen has an octet. We don't need to make multiple bonds in this particular case. Looking at the formal charges, 2, 4, 6, 7. Bromine contributed 7. It got 7 out of the structure. Oxygen contributed 6. It ends up with 2, 4, 6, 7. So oxygen gets the negative charge like this. This whole thing is going to be negative. Diatomics are always linear. There's no bond angle here. We need 3 atoms to define a bond. And so these are just linear structures. Let's move on to chlorate. Chlorine is 7 electrons, 3 oxygens, each is 6, so 3 times 6 is 18 electrons, and then -1 charge, this is 1 extra electron. And so this is going to give us 26 electrons altogether. Now chlorine is pretty electronegative, chlorine's a pretty good oxidizer, but in this case, we haven't combined with oxygen. And so chlorine's going to go in the center because even though it has a fairly high electronegativity, it's less electronegative than oxygen. And we'll throw the oxygens out here, something like this. Oxygen doesn't like to form single bonds, so we wouldn't do a structure like this to itself. It could bridge to other atoms, but it doesn't want to bridge to itself. This is called a peroxide bond. Then complete the octets. What am I doing? I did 4 oxygens, so it'd only be 3 oxygens. Let me erase one of those. So what we end up here with is 8 times 3 is 24, and then we have 2 left over. That's 26 electrons. So in this case, everybody has an octet, but let's take a look at the formal charges. Formal charges are going to be this. It's going to be minus. It's going to be minus. This is going to be minus because it's 2, 4, 6, 7, each of these. And this chlorine is going to be 1, 2, 3, 4, 5. This is plus 2. What did I say about plus 2 and minus 2? Plus 2 and minus 2 are kind of high as far as formal charges go. This whole thing adds up to minus 1. Plus 2 minus 3 gives us minus 1. So the formal charge is a little high on this. Now, chlorate can do something called expand its octet to reduce formal charges. Let's see what the book did. The book did not expand the octet. So I'm not going to expand the octet. In Chem 1A, you'll do this, possibly. Depends. In Chem 1A here, if you look at chlorine, it's got 2, 4, 6, 8, 10. It's expanded octet. But they expand the octet to reduce the formal charge. Here are 2 double bonds and a single bond. Here are 2 double bonds and a single bond. 2 double bonds and a single bond. Here, this is a good structure because they have all the electrons here. But if we look at the formal charge on this chlorine now, 1, 2, 3, 4, 5, 6, 7, it's 0. This oxygen, 1, 2, 3, 4, 5, 6, 7, 0. This oxygen, 1, 2, 3, 4, 5, 6, 6 and 6 is 0, 0. This oxygen is negative. So all the formal charges are 0 except for that oxygen over here, and this oxygen over here has a negative formal charge, like that. And so what they've done is they've expanded the octet. You know, when we look at the octet on chlorine, on all the oxygens, we still maintain an octet. But when we look at the octet around chlorine, it's got way too many electrons. 2, 4, 6, 8, 10, 12 electrons. 12 electrons, which is much greater than an octet. Now, if there were nitrogen, phosphorus, I mean, nitrogen, oxygen, you know, fluorine, we can't expand the octet. Carbon cannot expand the octet. But this is a bigger atom, so there's potential for expanding the octet. Formal charge is not discussed in this chapter, but it's critical. That's why I talked about formal charge. Then there's resonance forms for this as well. Here's a structure with the octet as is. This satisfies, but the charges are a bit high on this one. Look at the charges. Formal charge. Let's see what they say. Yeah, here they're expanding the octet. The same thing here, you know, sulfuric acid expanded the octet. Etc. Some examples here. Here's chlorate with the octet and then the expanded octet, and comparing the formal charges here. Yeah. So it says structure 5A, the one we just drew. does obey the octet rule, but places a formal positive charge on a relatively electronegative atom, chlorine, and has larger formal charges across all atoms than structure 5b. Structure 5b does not obey the octet rule, but chlorine is in period 3, or row 3 of the periodic table, and can accommodate an expanded valence shell. Additionally, structure 5b minimizes the formal charges on all atoms. Therefore, structure 5b is the most reasonable Lewis structure. This is what you'll do in Chem 1A. But in Chem 4, we're just going to leave it here. Chem 4, we'll just leave it. Relatively high formal charge there. And so when we look at chlorate, let me just draw the Lewis structure again. It doesn't matter how we orient this necessarily. And so I had the lone pair on the left, but it doesn't really matter. Everybody has an octet. Unfortunately, there's a kind of a high formal charge on chlorine, +2. -1 formal charges on oxygen, adds up to a net negative charge here. Let's look at the Vesper structure. There are 4 groups, a lone pair, 3 singles. And so we'll throw the lone pair in the plane and then one of the single bonds in the plane. That's going to put a single bond out of the plane here and a single bond into the plane here. And so here's our wedge and here's our dash. And then I'll just draw these out quickly as lines here. Again, the formal charges are kind of high all around. And so that's kind of something that we might worry about. But not for right now. Okay, so what is the EPG on this structure? EPG is tetrahedral. You know, we got 4 groups, so electron pair geometry is tetrahedral. The MG is not, because only these bottom ones have a bonded atom, so it's trigonal pyramidal. Now, trigonal pyramidal, you know, the ideal angle should be 109.5 degrees ideal. But we have a lone pair on the chlorine, which is going to distort it by about 2 degrees. So we expect the angle to be around 170 degrees. The oxygen, chlorine, oxygen angle here. It should be around 107. Okay, let's look at phosphate next and clear the drawings here. Phosphate phosphorus has 5 electrons. Oxygen is 6, but we have 4 of them. So 4 times 6 is 24 electrons. And then the 3 minus charge. So -3 charge is +3 electrons. And so this is going to give us 32 electrons altogether. All right, we're going to throw phosphorus in the center of this thing. And then we'll put in 4 oxygens here. Like that. Then we're going to complete the octet here. Like this. And that takes care of 32 electrons. Everybody has an octet. That's good. And so, but let's take a look at the formal charges. The formal charges, well, we're going to have formal charges because this whole thing carries a net -3 charge. And so each oxygen is 2, 4, 6, 7. So each oxygen is negative, negative. They're all the same, negative, negative. And the phosphorus ends up with 1, 2, 3, 4. It contributed 5. It's 1 short, so it's plus. So we have some formal charge there. Excuse me. We add up all the formal charges, you know, +1 minus 4 gives us -3, or 3 minus. So the whole thing's charge 3 minus. Now, there's formal charges, but at least everything has an octet. And octet usually wins unless it's boron. Boron is a loser. And octet's the primary concern, and then formal charge. Now, if you have multiple structures all with octet, then pick the one with the least formal charge, like we did for nitrous oxide N2O, which was the challenge or advanced problem. Now, when we look at phosphorus, it has 4 single bonds. And so phosphorus with 4 single bonds means it's going to be tetrahedral. And so 1 single bond in the plane. Oops. That's not supposed to be a wedge. It's supposed to be just a line. So 1 single bond in the plane like this, 1 single bond in the plane, 1 single bond coming out of the plane, and 1 single bond going in. So I'll just try to speed it up by drawing the lone pairs as lines. Like that. Whole thing carries a 3 minus charge. The formal charges are shown up there. So when we look at the EPG is tetrahedral. The MG is going to be the same because the bonded atoms also are tetrahedral as well. And the angle should not be distorted. There are no lone pairs on phosphorus, so we expect a 109.5 degree angle on that. Let's see how the book drew these. All right. I really don't like their the wedge and dash here. It's not conventional here. These are flipped. This is non-conventional. This is looking from the bottom. We usually look from the top or when we have models. What's really handy to have are model kits. And so if you don't have model kits, you can get 4 pencils. If you have 4 pencils, then you try to arrange them in tetrahedral fashion like this, and then look down at it. This is what you'll see here. If you look up at it like this, if you hold it up here, just try to make a tetrahedral arrangement of sticks, then you'll get this. So this is why I call it non-conventional. This is more conventional here. And so I would not draw them like this, and then I'd include the lone pairs, you know, in all the drawings. So I already commented on that. C3H70H. Now, you know, with these bigger organic molecules, sometimes it's just better just to you know, just to try to connect the pieces. So I got 3 carbons. So let's try to just connect 3 carbons together like that. And then 7 hydrogens. So carbon likes to form 4 bonds. So 1, 2, 3, 4, 5, 6, 7. And so this carbon has 4 single bonds. This carbon has 4 singles. This carbon has 3 singles, but we'll throw an OH on there like this. An OH. And so this is called propanol here. And so I didn't total up the electrons, etc. I just tried to do it based on familiarity with these types of structures. The more of these you see, then So Lewis structure. Situation with Lewis structure is it doesn't give us the three-dimensional. Like this first carbon's tetrahedral. And so we could try to draw this out like this. And so try to draw out 2 in the plane, 1 coming out, 1 going in like that. It's tetrahedral. The next carbon's going to be tetrahedral. So this is bonded to 2 hydrogens out over here. Now, what we're going to do is we're going to put 2 in the plane like this. And so this is in the plane, this is in the plane. And then we're going to stick 1 out like this. So this is going to wedge out, and this is going to wedge in. These are the 2 hydrogens. So this is a tetrahedral that's been tilted, you know, like here. You can see it. Yeah. And then we'll do another tetrahedral, but the 2 in the plane will form a zigzag. So what we want is we want to form a zigzag like this. And that's going to mean 1 is going to wedge out like this, and the other is going to wedge it in like that. So we'll throw in the hydrogens here. And then that's going to go to the oxygen. Now this oxygen is also tetrahedral. And so the 2 in the plane that we'll make are the bonds. And that means 1 lone pair is going to wedge out like this wedge here. 1 lone pair wedges out like this wedge. And 1 lone pair is going to wedge in like this wedge here. And so we see this when we have long organic chains, we'll try to zigzag them like this. And then that results in these kind of wedge out, wedge in type scenarios at the end. And so this one's tetrahedral, EPG, MG is tetrahedral, and angle should be 109.5. This one, EPG is tetrahedral, MG is tetrahedral, and the angle should be 109.5. This one's the same thing, tetrahedral, tetrahedral, 109.5. So each carbon's the same. The carbons are going to be the EPG, tetrahedral, the MG, tetrahedral, and the angle, 109.5. Now the oxygen here is the EPG is tetrahedral. It's got 4 groups, 2 single bonds and 2 lone pairs. Those 4 groups are tetrahedral, 3 groups are trigonoplanar, 2 groups are linear. Now the MG is going to not be the same because when we look at the atoms, it's just going to be bent. It's going to be bent at 109.5 degrees. But there are 2 lone pairs on oxygen. 1 lone pair is going to crush it to 107. The second lone pair is going to compress it to 105. And so we expect the bond angle to be about 105 degrees in this particular one for the oxygen. The carbons are all the same. So that was propanol. Let's look at this one here. Okay, C2H5NH2. Okay. Clear these drawings here. So what I'm going to do is I'm going to do another carbon chain. So let's go carbon. Actually, in the Lewis structure, we don't have to do it 3-dimensionally. So Lewis structure, you just draw whatever, you know, whatever works. So we'll put 2 carbons and then throw a nitrogen on the end. And then H5, C2H5. So 1, 2, 3. Carbon likes to form 4 singles, or 1 double, 2 singles, or 2 doubles, or 1 triple and 1 single. When it's neutral, you know, when there's no charge. Shouldn't be any charge here. So that's 3, 4 hydrogens, 5 hydrogens, and then N, and then this one should have, let's say 2 hydrogens here. Okay, that's it. But now you have to know that there are no formal charges here in these organic chains. So this has to have a lone pair. Otherwise, nitrogen would end up with a charge. This keeps nitrogen's formal charge at 0. So this is the bonding environment. Nitrogen likes to form 3 singles and a lone pair, or it could form a double, a single, and a lone pair, or a triple and a lone pair. Or if there's a charge, then they could form 4 bonds, you know, like in ammonium, you know, if there's a charge. All right, so this is tetrahedral, this is tetrahedral. So we get some practice drawing this. And so this first tetrahedral, 2 in the plane, like this, 1 wedged out, 1 wedged in. Down. That's going to a carbon. And so we'll zigzag it like that, and then wedge one out. That's going to be hydrogen there, and wedge one in. This is going to be hydrogen here. And then this is going to go to the nitrogen. Now the nitrogen's tetrahedral also. And so we could put two in the plane. But for nitrogen, we like to put the lone pair in the plane. We like to put the lone pair and one of the bonds in the plane, and then wedge one in and wedge the other one in. The reason we like to show it like this is because it shows the trigonal pyramidal geometry around the nitrogen a little easier. And so conventionally, we put the lone pair here in the plane and a bond in the plane. And that way, when we look at the EPG is tetrahedral, but the MG is trigonal pyramidal. And the angle is ideal is 109.5 because the tetrahedral angle is 109.5 degrees, but we got that one lone pair, and that one lone pair is going to compress it by about 2 degrees. So it's going to be about 107 degrees. That's going to be the CNH angle or the HNH angle. And both should be about 107 degrees here. And so that would be the N nitrogen here. This is called an amine. Amines are like ammonia. You know, carbon and hydrogen have similar electronegativities. Electronegativity of carbon is 2.5, electronegativity of hydrogen is 2.1. So having this, what we call alkyl group here, doesn't change the basicity of this by much. You know, ammonia is a base. If we had a hydrogen here, you know. And so the amines are ammonia-like bases. These are organics. So this is called ethyl. This is an ethyl amine. See how they drew it. Oh, they didn't draw it. They just named it. And this Lewis structure is not accurate. It looks like the bonds are 90. It looks like the bond is 90 degrees. It looks like T-shaped. It's not T-shaped. And this would be more accurate, three-dimensional drawing of this. Okay, I missed it. How do you know if the angle is distorted or not again? If there's a lone pair, here as one of the positions, then it'll distort it. And so this is tetrahedral with a lone pair in one of the positions, and then the angle is going to be distorted. Normal tetrahedral angle is 109.5. Now, it has to be on the same atom. If the lone pair were over here, then it doesn't matter. It's not going to impact it. So when we're looking at nitrogen, if there's a lone pair on nitrogen, that's going to impact the angle. Yes, the lone pair distorts the angle because what happens is in a bonding pair, there are two atoms that are trying to fight for the electrons. In other words, there are two atoms trying to pull the electrons towards it. And so bonding pair is distributed between two atoms. Here. So distributed between two atoms. And so carbon's trying to pull it, nitrogen's trying to pull it, hydrogen's trying to pull it, nitrogen's trying to pull it. So there's a tug of war. Here, nitrogen doesn't have to fight anybody. Nitrogen gets all of it. Since it gets all of it, then it gets compressed. So this is a bigger balloon because nitrogen gets all of it. Whereas here, this balloon's being stretched out. You know, hydrogen's trying to pull on the balloon, carbon's trying to pull on the balloon. And so this is why lone pairs result in distortion, because the lone pair is not being fought over by another atom. A lone pair is strictly on nitrogen, so the balloon is not being distorted or pulled or in a way. And so because of this bigger balloon size, the lone pair is a bigger balloon, it's going to push these other balloons in a little bit. And as it pushes it in, that's what causes the compression of the angle. Yeah, so that's correct. The lone pair does distort the angle. All right, here's another one. It's a C2H2, and so let's try that. And so we have two carbons and we have two hydrogens. So we'll throw a hydrogen on each carbon, but note that there's not enough electrons there. You know? And so the way we do organics oftentimes is we know carbon can form two singles and a double, or a triple and a single. And so this has got to be a triple and a single. That's going to give 4 bonds. It's going to give 0 formal charge. We need 0 formal charges for this to add up to neutral. And so this has got to be it. It's got to be HC triple bond CH. And so we just fill in the bonding depending on what we have. There are no lone pairs here because carbon doesn't usually have a lone pair like nitrogen, you know. This is how I visualize this. Carbon, 4 singles. Carbon has 2 doubles. Carbon has a triple and a single, like that. Nitrogen has a lone pair and 3 singles. Or nitrogen has a lone pair and a double and a single. Or nitrogen has a lone pair and a triple. That's how we visualize. Oxygen has 2 lone pairs. This is with 0 formal charge. If we throw in formal charge in there, then it becomes more, you know, there are more choices. Oxygen has 2 lone pairs, and so it could form 2 singles. Or oxygen can form a double, like that. In other words, oxygen likes to form 2 bonds, but you know, it could also, if there's a formal charge, it could form 1 bond, like in hydroxide I showed earlier. Or it could form 3 bonds, like in hydronium, where it has a lone pair and 3 singles, but it's got a positive charge. Same thing with nitrogen. In ammonium, it could form 4 bonds. In amide, we did those earlier. If you recall, we did ammonium and amide and ammonia. You know, and so to look at the different bonding arrangements there. So this is what we call acetylene. Acetylene, we look at each carbon. And so when we look at each carbon, that's what we call a central atom. A central atom bridges other atoms. So we're looking at carbon here. This is going to be, the EPG is going to be linear because we can't treat this as 3 separate groups. It's 2 groups, a triple bond group and a single bond group. So if we have 2 balloons, then the 2 balloons want to be linear to spread out. That's going to give us a 180-degree angle. The MG is the same. It's going to be linear because the atoms follow the same structure. And the angle here, this should not be distorted. There are no lone pairs to distort this, so it's going to be 180 degrees here. Now, double bonds and triple bonds take up more space. Triple bond takes up more space, but still it's going to be 180 degrees, you know, even if the triple bond takes up more space. Now, this carbon's the same. You know, 2 carbons are the same. Now, when we look at HCN, we have a choice. We could do this like the organic way of making Lewis structures, or we could do it like our standard inorganic. Let's do it our standard inorganic way of doing Lewis structures. Hydrogen has 1 electron. Carbon has 4 electrons. Valence, not total. You know, carbon has 6 electrons total. Nitrogen has 5 valence electrons, or 7 electrons total. We're just looking at the valence electrons. So altogether, we're going to have 10 electrons for this. Now we'll throw carbon in the center because carbon is the least electronegative. And then we'll complete the octet to nitrogen because nitrogen is the most electronegative. And so that takes care of 2, 4, 6, 8, 10. That's 10 electrons, but what's the problem with this structure? Can you see it? What the problem is with the structure? 2 problems, but the most serious problem is what? The most serious problem is this carbon here. It only has 2 4 electrons. 4 electrons is less than an octet. That's not good. Yeah, carbon, we need another. Actually, carbon likes to form a total of how many bonds? Carbon likes to form a total of 4 bonds. So even if we add one more, it's not enough. So what we're going to have to do is we're going to have to add 2 more, like that. And so what's going to result is it's got to be a triple. Yeah, we could have figured that out using the organic way. You know, just kind of putting these together. But it's going to look like this. No formal charges. All the formal charges are 0. The second problem with this is the formal charges are all screwed up. But all the formal charges look good. That's what we expect when we use these type of bonding structures. All the formal charges should be 0. Well, anyway, this is a single bond group and a triple bond group. So again, it's just like the previous problem. The EPG is going to be linear. We can't split up a triple bond into 3 separate groups. And that's going to set the angle of 180. The MG is going to be the same, linear, and the angle is going to be 180 for HCN. C2H2 is called acetylene. This looks like that. HCN is hydrogen cyanide gas. If it's aqueous, we call it hydrocyanic acid. It's hydrogen cyanide. It's linear 180. Draw the Lewis diagram of certain compound has the element E as its central atom. The bonding and lone pair electrons E are shown. What is the molecular geometry around E? So after a while, you'll see, you know, these. You know, I would have drawn it like this. The lone pair in the plane, one of the bonds in the plane, the other bond sticking out and one sticking in. So when we look at the molecular geometry, we're looking at it, bonded atoms A, B, C. The lone pair doesn't count. And so the molecular geometry here is going to be what? Molecular geometry here should be trigonal pyramidal. You know, trigonal pyramidal. That's correct. That's good. Trigonal pyramidal. Let's go on here. Draw a central atom with whatever combination of bonding and lone pair electrons is necessary to yield an angular bend structure around the atom. This one is not trigonal planar. This one looks trigonal pyramidal as well. And so let's see how they're doing it here. Oh, wait, they're doing this trigonal planar. That does not look trigonal planar to me. It looks like there's a lone pair on the top. Why do I think that? Well, I think that because it's pushing the reds down. Do you see how the reds are kind of being tweaked down? It's because of lone pair. A lone pair is kind of a big balloon pushing these 3 red balloons down. If a trigonal planar would look more like, that's just doesn't look trigonal planar to me. Let's see if they have trigonal pyramidal. What do they call that? Do they call it pyramidal or planar? They call it trigonal pyramidally. Well, this is wrong. There's just no Y at the end, trigonal pyramidal. That's okay. Those are a little bit ambiguous, so skip those because it wasn't so clear. Is that pyramidal or planar? This is easy. This is tetrahedral, right? Tetrahedral and tetrahedral. Tetrahedral, tetrahedral. This is salicylic acid, which is aspirin. Some aspirins will get rid of the acid, so it's easier on the stomach and make what's called an ester. You know, here's the acid part. COOH is carboxylic acid. And so rather than having an H here, they'll put like a CH3 or something like that. And that will make this a lot less acidic, which is going to be easier on the stomach. Estimate the bond angles. So A, what do you estimate the bond angle here is? When I look at A, I look at, this is trigonal planar because it has 3 groups, single bond, double bond. Now double bond group takes a little more space. So ideal, this is 120, but since a double bond takes up more space, it might push it to 122. So 120 ideal, maybe 122 because of the double bond, the extra pair of electrons there. So what do they do with A? They didn't do the distorted, just the ideal 120. Let's take a look at B. B is, this is going to be bent. This is tetrahedral EPG, but the MG is bent. Ideal is 109.5. C, this is tetrahedral EPG and tetrahedral MG, so 109.5. D, this should be trigonal planar, 3 groups, you know, double bond, 3 groups, 120. But the double bond takes up more space, so that should expand the angle by about 2 degrees, so 122, maybe. But we aren't doing the distortion, so 120, 109, 109, 120. It depends on how many regions of electron density, single bond, double bond, a lone pair, etc. This is lactic acid here. Cinnamaldehyde. Cinnamaldehyde, like cinnamon. Okay, when we look at C, this is trigonal planar, you know, EPG. Double bond, single bond, single bond. It'll be distorted because the double bond takes up more space. Again, B is going to be, this is going to be trigonal planar, 3 groups, single bond, double bond, 120 ideal. This is also going to be trigonal planar, single bond, double bond. And so these are all trigonal planars, flat. Let's see, 120. Amphetamine is an amine. It has this nitrogen, like ammonia, like trigonal pyramidal thing here attached to this. So this should be tetrahedral, EPG, trigonal pyramidal, MG, and an ideal angle of 109. It would be tetrahedral, ideal 109, and it should stay ideal. This one will be distorted because of the lone pair. Lone pairs and double bonds, they distort about the same amount. All right, which of the following, okay, which of the molecules are non-polar with polar bonds? So all of these have polar bonds. So this one, A should be polar because if these have polar bonds, they don't cancel each other out. If this were linear, it would, but this is bent. So bent does not cancel each other out. And so that should be polar. B should be non-polar because they cancel each other out. So I'll just give a quick example there. Polarity is important because this, okay, let's just try to draw this our standard way. Our standard way of drawing this type of scenario is the bonds are in the plane like this. And then one lone pair wedges out this, and one lone pair is wedged in. And so you try to draw it the same way each time. And that minimizes the number of variations that you're accustomed to seeing. You know, once you get those drilled down, then you can draw it any way you want. Try to recognize it. But here, if they're bond dipoles, those bond dipoles aren't going to cancel out. So let's say we had a bond dipole pointed this way, and a bond dipole pointed this way. The net molecular dipole is going to point this way. Okay. Whereas this is linear, and so if I had a bond dipole pointed this way and a bond dipole pointed this way, then it's going nowhere because, you know, they're equal and opposite. Here, this is trigonal pyramidal. You know, trigonal pyramidal, we draw the same way, kind of like this. And then the lone pair, this lone pair and this bond in the plane, this one wedged out, this one wedged in. And so the arrows aren't going to cancel out. But whereas this one, the arrows will cancel out, you know. Here, it depends. It can be either pulling or one way or the other. It doesn't matter. Let's on this one, let me pull it the other way. Make it easier. So here, if there's a tug of war, this A is pulling, this A is pulling, and they're all equal in strength, and then B's not going anywhere because these are going to cancel each other out. And so this is non-polar. This is polar. This is non-polar. This is polar. This is going to be, oddly enough, non-polar. It's because of the tetrahedral shape. It's not because of the square planar shape. It's not square planar, it's tetrahedral. And if A is pulling up and A is pulling down this way and A is pulling that way and that way, then it's not going to go anywhere. This is spherical symmetry. So if you think of these two pulling this way and these two pulling the opposite, they're going to be equal and opposite. So it's going to cancel each other out. And so this comes out to non-polar. This is same, I don't know. Is the carbon tetrachloride molecule CCl4, which contains 4 polar bonds, polar or non-polar. Well, carbon tetrachloride, even though it has very polar bonds, we look at the structure, carbon's in the center, and then we got 4 chlorines on there. 2 in the plane like this, 1 wedged out like this, and 1 wedged in. This chlorine's more electronegative, so chlorine's pulling the electron cloud away from carbon. But the situation here is if chlorine's pulling this way, this way, this way, and this way, nothing's going to happen. It's not going to move anywhere. And so this ends up being non-polar because in a tetrahedral arrangement, we have spherical symmetry. They're all going to cancel out in 3 dimensions. A little bit hard to see, but the bonds are symmetrically arranged, which makes the molecule itself non-polar. Describe the shapes and compare the polarities of HF and HBr. The shapes are linear. All diatomic molecules are linear. In each case, identify the end of the molecule that is more positive. Well, fluorine's the most electronegative, so both molecules are linear. HF is more polar. H end is positive. Yeah, fluorine end would be negative and bromine end would be negative. So good electronegativity. Sketch the Lewis diagram of the water molecule, paying particular attention to the bond angle, using arrows to indicate the polarity of each bond, and sketch the methanol molecule. All right, so first let's sketch water. After a while, you probably go ahead. We know water has 2 lone pairs and 2 single bonds. So let's put the single bonds in the plane, this. And then 1 lone pair will wedge out like this, and the other lone pair will wedge in like that. And so this is our standard tetrahedral EPG, but the MG is going to be bent like this. Now let's look at methanol. And so methanol, let's do the same thing with the water, except methanol is going to have carbon here on the end, like this. Now, there are different ways of drawing out methanol. If I did methanol CH3OH, I could mimic this, but I'm not going to mimic that, maybe. Or maybe I will. And so this carbon is going to be tetrahedral. And so it's going to have 2 in the plane and then 1 sticking out and 1 wedged in like this, you know, something like that. But I could also draw this and then alternative way, you know. I'll just draw it the same way as this. Yeah. Now, methanol and water are very similar. The reason is because of this. The oxygen is going to build up negative charge, and the hydrogens are going to build up positive charge here. Yeah. Oxygen is going to build up negative charge. Now, the hydrogen is going to build up positive charge, and this carbon is going to, the carbon and hydrogen have similar electronegativities, so this carbon is also going to build up positive charge like this here. And so in terms of polarity, you know, both of these are polar molecules. And so oxygen is more electronegative, so it sucks the electron density. So we can draw these arrows with the positive tail. But the exact same thing happens here. And since carbon and hydrogen have comparable electronegativities, we're going to get the same kind of polarity here. And so water and methanol are very similar in terms of polarity. Predict the approximate shape of both molecules around the oxygen. Also predict relative polarities. And the relative polarities are going to be very comparable. So the net molecule dipoles like this in methanol, which is very similar to the net molecule dipole in water. Here. Good. So what did the book say? Both molecules are polar because of the bent structure around the oxygen atom and the concentration of negative charge near the highly electronegative oxygen atom. The carbon-oxygen electronegativity difference is slightly less than the hydrogen-oxygen electronegativity difference. So methanol is just slightly less polar than water. Yeah, just slightly less polar than water. They just drew the Lewis structures. I tried to draw the three-dimensional wedge dash diagram. And I wouldn't have drawn methanol like that unless I wanted to mimic what I drew for water. Normally when I would draw methanol, I'd draw it like this. The carbon on the end here, and this is tetrahedral, so two in the plane, one wedged out, one wedged in. So these are all hydrogens here, and then we have the oxygen here, and then we'll draw two in the plane like zigzag, and then one wedged out like this, and one wedged in like that. And so this is the way I normally draw methanol, but I just tilted it up like that. Which species have tetrahedral shape? Well, we did this one. It's a very similar one, BF4 minus. This is BH4 minus. This is tetrahedral. Tetrahedral. Have tetrahedral shapes. Now, shape is the Mg. Shape is not the EPG. And so this has a tetrahedral EPG. You know, two lone pairs, two single bonds would be tetrahedral, but the Mg is going to be bent, because we don't see the lone pairs in the molecular geometry. This also is going to be a tetrahedral EPG, but the shape should be trigonal pyramidal. This is going to be tetrahedral. This is going to be trigonal planar. Which species are linear? Not this. This is not linear. This is bent because of the two lone pairs. This is not linear. This is not linear. This is linear. Now, beryllium, like boron, doesn't get a octet. You know, beryllium's a metal. And so beryllium and boron do not have an octet like this. If we look at this boron, look, boron does not have an octet because boron would have to take electrons away from fluorine. Well, fluorine's the most electronegative. Boron's not going to be able to do that successfully. Which neutral molecules are polar? Neutral, that's not, this is going to be polar because that's bent. This is going to be polar. This is going to be non-polar here. Identify all species that have a trigonal planar. Trigonal planar is three groups. This is four groups, four groups, four groups, four groups, two groups, linear, three groups, trigonal planar. This would be it. What distinguishes an organic compound from an inorganic compound? Organic compounds all contain carbon. Inorganic compounds, with some exceptions, do not contain carbon. Yeah, except like CO2, you know, CO2, those are considered inorganic. Identify the hydrocarbons among the following. Hydrocarbons are compounds of just carbon and hydrogen. This is an alcohol. I know, this is methanol, actually. This is a hydrocarbon. There's only carbon and hydrogen. Hydrocarbon, this is an amine, remember with the nitrogen and hydrogen in there. This is a hydrocarbon here, just carbon and hydrogen. Hydrogen and hydrocarbons and carbohydrates are similar terms. Both are made by combining words or parts of words. Can you guess what the words or parts of words are in each case? Can a carbohydrate be an example of a hydrocarbon and vice versa? No, hydrocarbons aren't going to contain oxygen. Carbohydrates, the reason it has this name, carbohydrate, is because of the hydrogen to oxygen ratio. The hydrogen oxygen ratio in carbohydrates is 2 to 1, like water. And so let's look at some carbohydrates right now. Let's see if I can think of one, like glucose, C6H12O6, 2 to 1. Do you see that? 2 to 1. Let's take a look at well, this is glucose. Let's look at sucrose. Sucrose would be C12H22O11. Look at the hydrogen to oxygen ratio. It's 2 to 1. So this is sucrose. This is glucose. And so they have this hydrogen to oxygen ratio of 2 to 1. So carbon with kind of a hydrate, but it's not, there's no water in there, of course. It's just a 2 to 1 ratio. Distinguish between the structure of an organic molecule as given by its Lewis structure and the three-dimensional shape. Lewis structure doesn't have to be three-dimensionally accurate at all. The structure of molecule simply describes in 2 dimensions the relative positions of how its atoms are bonded. The three-dimensional shape of a molecule results from its structure and is the arrangement of the atoms in 3-dimensional space. In other words, this is the VSEPR. Lewis structure, what we do is we analyze the Lewis structure, the 2D model, and convert it into 3D. Why can a zigzag chain of carbon atoms be drawn as a straight line in Lewis diagram? Well, in Lewis diagram, we don't care. You know, but in 3-dimensional shapes, we care. Also, it depends on the angle you look at it, you know. Depending on the angle, although I can just show you really quick, it depends on the angle you draw it. Yes, it could be, it could be zigzag, but depending on the perspective you look at it, it might not look zigzag at all. It might look straight. How are alcohols and ethers similar to water in structure and shape? What distinguishes between alcohols and ethers? All right, let's get to that in just a minute. Let me just show you something here. So I told you about the zigzag. The zigzag, that's very important because that's what we do, you know, when we're drawing these and making these things. Okay, here you can see the zigzag, you know, and what we do is we put one in the plane. So I kind of drew it like this. I need to tilt it I need to rotate it just a little bit more this way. The zigzag isn't quite zigzag the same way I did it, but it's all right. You can kind of see how it's zigzagged here. It depends on the perspective you look at it. Okay, if we look at it here, does it look zigzag at all? No, it looks straight line. And so it depends on what angle you're drawing this from. If we draw it like this, then it totally looks straight line. Straight line, but it really isn't straight line because when we tilt it on its side, we can see it's not straight line, it's zigzagged like that. Okay, alcohols and ethers are very similar. You know, alcohols, the only difference between an alcohol and ether is alcohol COH, ethers are COC. That's it. Let me see what they say here. So an alcohol is going to have a COH link, and there's going to be a lone pair here, and the carbon's going to be bonded to other stuff. An ether is going to have a COC link. These carbons are going to be bonded to other things. And there's going to be two lone pairs on this. So they're both tetrahedral EPG, the oxygen is, and they're both bent MG. And so in that way, they're very similar, you know, in terms of the structure. We can build one pretty quick in Spartan too. All right, so if I want to make this into an alcohol, I just will add an OH to an O and an H here. That's an alcohol. If I want to make this into an ether, I'll get rid of the H here and put another. This is an ether, but you know, the oxygens can be very similar. How do carboxylic acids differ from other acids such as hydrochloric, sulfuric, and carbonic? Well, all carboxylic acids have the COOH group. Hydrochloric does not, sulfuric does not, carbonic, let's see, does not. And so carboxylic acids have the COOH group. Now the structure of the COOH group doesn't look like this, you know. Structure looks totally different. Look at the structure. Take a look at the structure of the COOH group. So let's throw, let's get rid of some of this. Get rid of that. Let's get rid of this one. Let's make a COH group. Now the COH group is going to have a trigonal planar carbon like that. And then it's going to have a terminal oxygen like this, and it's going to have a bridging oxygen like this. And so it's going to look like this. We'll replace this calculated version here. So you can see this trigonal planar. This is the COOH group here. Like that. That would be it. Distinguish, okay, these ones I'm not going to worry about here. Classify each true or false. Molecular geometry around an atom may or may not be the same as electron pair geometry. That's true. You know, they don't have to be the same. Electron pair geometry is the direct effect of molecular geometry. That's false. Molecular geometry is the direct effect of the electron pair geometry. If the geometry, this is why we do electron pair geometry. We always do EPG first, and then molecular geometry second. If the geometry of a molecule is linear, the molecule must have at least one double bond. False. A molecule with a double bond cannot have a trigonal pyramidal geometry around the double bonded atom. That's actually false. Let's see what they say. This is actually false because of expanded octets. Trigonal pyramidal geometry around the double bonded atom. Yeah. The Chem 1A be a little bit different. A CO2 molecule is linear, but an SO2, yeah, SO2 has a lone pair. You know, carbon has only 4 valence electrons. Sulfur has 6 valence electrons. So there's an extra lone pair on sulfur, which makes this bent. That's true. A molecule is polar if it contains polar bonds. That's false, you know, because if they're equal and opposite, they cancel. So what we have to have is we have to have polar bonds that don't cancel each other out. And then it would be polar, non-polar. A molecule with a central atom that has one lone pair of electrons is always polar. This one is a tricky question. You know, your book is going to say true, but there are cases where it could be false. They just aren't in this book. A molecule with a central atom that has two lone pairs and two bonded pairs is always polar. That's true. It's always bent. Yeah, as they are in this book. Now, of course, if you go and look at, you know, this, I don't particularly like these questions here because they're okay because they're in this book. But if you look in another book, there could be examples, exceptions to these rules. So I don't take these as rules here. Carbon atoms normally form 4 bonds. That's true. Hydrogen atoms never form double bonds. That's true. One kind of C6H12 molecule has its carbon atoms in a ring. Draw the Lewis structure. All right, so if they're telling us this is a ring, then we'll just draw a 6-membered ring like this. So C, 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 C. Okay, so there's 6 carbon atoms, 2, 4, 6. And then carbon likes to form 4 bonds. So it looks like we have 2 hydrogens to each carbon. This. And so this will give us C6H12. C6H12 is called cyclohexane. And so that would be the Lewis structure here. This is the Lewis structure of cyclohexane. Now, each of these carbons is tetrahedral, so this is not flat. It's not a flat ring. This ring has an odd zigzag pattern to it as well. And so let's take a look at that odd zigzag pattern here on this particular ring. So I'm going to go with a new build here. And so we're going to build a ring of tetrahedral carbon atoms. Hopefully I can close the ring. Let me see, can I close the ring? Maybe. Close the ring. I need to form this as a bond here. Can I group those into a bond? Yeah. Okay. And do you see that weird zigzag pattern? This weird zigzag pattern is called the chair. Do you see? It's the chair. It's kind of like a chair, I mean, in a way. This is the chair. There's also one other one called the boat. If I twist these, let me twist these bonds here. Can I twist that? Oh, actually this got screwed up here. This is supposed to be one bond. That's all right, but that's the chair, kind of see it. Okay, draw the Lewis structures for the 5 acids of bromine. All right, this is probably good. It's a place to take a break. So let's take a break and then we're gonna look at number 70 here to do next. Okay, let's take a look. At the 5 acids here. Now, you have to look at some patterns here and rules. Now, one of the rules is regarding acids. I already mentioned this before. The H goes on the most electronegative. And that's a rule we can use. here we have no choice. The H has got to go on BR. And so for HBr, it's going to look like this, HBr. H contributes 1, BR contributes 7. And BR ends up with an octet, H ends up with a duet. And so this is a structure of HBr. Now this is very tricky because you would think the H does the same thing. The H should bond to bromine, but the H does not bond to bromine in this. The H is going to go on the most electronegative. So if we're comparing bromine with oxygen, oxygen's more electronegative. And so the H is going to go on there. That's going to make oxygen the central atom here, but it's just weird in this particular structure here. Now let's see how many electrons we have. So bromine is 7 electrons. Oxygen is 6 electrons, and hydrogen has 1 electron. And so it gives us a total of 14 electrons. And so actually we can complete the octets to everything like here. That will give us 14 electrons. All the formal charges are 0. But this is odd because it looks like H is bonded to bromine. H is not bonded to bromine. H is bonded to oxygen here. That's it. And so this is the structure. This is a hypobromous acid. Now let's look at bromous acid here. When we look at bromous acid, H has 1 electron. Bromine has 7 electrons. And now we have 2 oxygens. That's 6 each, so that's 12 electrons. 19, 20 electrons for this. Okay, now we have a choice here. Here we had to put the oxygen in the center, but here we're going to try to put the bromine in the center. And the H is not going to bond to the bromine. It's an acid, so the H should bond to oxygen. And so we'll have an OH there. And then we'll have an O here. So now they're 2 central. This oxygen is bridging, this bromine's bridging, this oxygen's terminal. And let's complete the octets to the terminal atoms first. So we got 20 electrons. We'll complete it to this one. That takes care of 2, 4, 6, 8, 10, 12 electrons. And then let's complete it to this oxygen, 14, 16, and now the bromine, 18, 20. So it worked out. Everybody has an octet in this particular structure. Now, are the formal charges all 0? And so when we look at this oxygen, you probably recognize this oxygen now has a negative formal charge, 2, 4, 6, 7. This bromine, 2, 4, 5, 6. Bromine contributed 7, so it's short. This oxygen is 0, this hydrogen is 0. So this ends up with a formal charge here. We can get rid of that formal charge if we expanded the octet. And so in Chem 1A, you might do something like this, where we expand the octet. That is, now bromine's going to have more than an octet, like this. But the advantage of bromine having more than an octet is all the formal charges are 0. So oxygen is 0, 2, 4, 6. Bromine 0, 2, 4, 5, 6, 7. Oxygen 0, 2, 4, 6. And hydrogen 0, 1. And so this is the expanded octet. You know, so that's often done. Our book does not expand the octet. Our book leaves the formal charge, so our book is going to have it like this. Let's take a look. The National Library of Medicine. What does the National Library of Medicine have? The National Library of Medicine has what we call an expanded octet. Do you see they've made a double bond here to expand the octet on bromine? They don't have the lone pairs there. When we can expand the octet, now when can we expand the octet? We can expand it with 3rd period, 4th period, 5th period. We cannot expand the octet with second period atoms. No, they're too small. The third period, fourth period, fifth period are bigger atoms, so possibility of expanding octet. So in Chem 1A, you might write the structure like this, but in Chem 4, you're going to write it like this. When you look at it, when you search the internet, they're all going to be written like this. Let's see what we got here. Maybe this is too confusing. Okay, let's go to bromic acid. HBrO3. Okay, it looks as if the H is bonded to bromine. It's not. The H is bonded to oxygen. Yeah. And so what we'll do is we'll throw bromine in the center. And then we'll put 3 oxygens around it, like this. And then one of the oxygens will have the H bonded to it. And then let's complete the electrons here. Hydrogen is 1 electron, bromine 7 electrons, 3 oxygens is 18 electrons. So all the other 26 electrons. Complete the octet to the terminal atoms first. And then if we have leftovers, complete it to this bridging oxygen here. So that's 8 times 2, 16, 18, 20. It's 20, so it's 22, 24, 26. So this would be it. Now the structure for this, it's all octets, that's good, except the formal charges. This is negative, this is negative. This bromine, 1, 2, 3, 4, 5. This bromine is +2. This oxygen is 0, and this hydrogen is 0. So the bromine kind of has a high formal charge of +2. And so in this case, we're probably going to form double bonds to expand the octet and reduce the formal charge. But for us, we're going to just leave it there. How about, let's take a look online and see what they have online for bromic acid. You see they expanded the octet. They formed double bonds here in bromic acid. You can see it in Wikipedia. Unfortunately, they didn't write the lone pairs, but when they do this, the formal charges go down. Let me see if they have one where they do the lone pairs in there. Which would be nice if they did. Here's one, they didn't expand the octet, so you could have a high formal charge on the bromine there. There's a problem when they get more advanced, when you get to more advanced classes, they don't usually write the Lewis structures like organic chemists because they already know what it is and they can save time by not writing it in there. Here they show all the formal charges are actually none of these do. So they figure once you're at this level, then you should be able to figure out where the lone pairs are and how many there are, you know. So this oxygen is 0, 2, 4, 5, 6 is 0. This oxygen is 0, 2, 4, 5, 6 is 0. This oxygen here is actually 0, 2, 4, 5, 6, that's 0. Now this bromine is 2, 4, 6, 7, it's 0. All the formal charges are 0 if we make 2 multiple bonds there. The problem is bromine now it's going to have more than an octet, 2, 4, 6, 8, 10, 12. There's 12 electrons around it, which is much greater than an octet. But that's okay because it's third period, fourth period, or actually third, it's below. This would be fourth period. It's okay because this is fourth period. Fourth period is okay. That is the fourth row or the fourth shell. It's okay to expand the octet. This is called an expanded octet. For second period, it's not okay. You know, carbon, nitrogen, oxygen, fluorine will not expand the octet. Perbromic acid. Okay. So once again, it's an acid, so the hydrogen is going to go on the oxygen. The hydrogen is not going to go on the bromine. There's no net charge. So, you know, after you get, it's probably best to do it, counting up the electrons. 1 electron. Bromine is 7 electrons. 4 oxygens. 4 times 6 is 24. It gave us 32 electrons. I forgot to do the structures. This is tetrahedral. This minus, minus, oops, there should be an H on one of these. Doesn't matter which one, which of the 4 oxygens you put the H on. Like that. But leave it there. Once you pick one, leave it, don't move it. And so I'll pick this one, it's here. I have 32 electrons, so how many have I used? 2, 4, 6, 8, 16, 24, 32. This is 32 electrons. Bromine's going to come out short. +1, +2, plus, 1, 2, 3, 4. It's going to be +3. That's very high formal charge. So when we look at perbromic acid, we probably are going to form double bonds here to lower that. But this is tetrahedral on bromine that's bent around oxygen. Bromic acid was pyramidal, you know, trigonal pyramidal around bromine. So let's take a look. This was bent. You see how they made the multiple bonds there. It's going to expand the octet around bromine, way too many electrons, but all the formal charges are going to be 0 in this case. We made 3 multiple bonds there. All the formal charges go down to 0. And so you'll probably see that. It's not to say that this is wrong, you know, your book is wrong. And it's not to say that this is correct. The bonding is a little bit more, you know, because the bonding, we have to look at it in terms of full quantum mechanics. Bonding, you know, this is one of the failings of Lewis structures and this kind of stuff is sometimes it's hard to describe it accurately. And so they just left all the formal charges here, you know. But note the hydrogen, except for HBr, the hydrogen is bonded to the most electronegative. In this case, oxygen. They never went beyond an octet. They don't expand the octet. No. And they just left the formal charges. They didn't calculate the formal charges because they didn't talk about the formal charges. Here they're saying, do the carbons are in a straight line? No, they're zigzagged. You know, the carbons are zigzagged. They're not a straight line. They're a tetrahedral. They can't be in a straight line. But it depends on what angle you look at it. All right, let's see. So benzene is a planar compound in which the carbon atoms are arranged in a hexagon. A Lewis diagram of this geometry. Let's take a look. This is benzene. It's flat. This doesn't have a chair shape like cyclohexane. Cyclohexane had that chair shape. This is just a flat ring because all these are trigonal planar. You know, this is trigonal planar, both EPG and MG. And so all these are trigonal planar. This whole thing is flat. Like this. Shows that the diagram does not describe the structure of benzene accurately. It doesn't describe it accurately because double bonds are shorter than single bonds. And in this particular case, we have a resonance form. Do that. Second. One second. Sorry, just 1 second. I'll be right back.
Mm-hmm.
Okay, I'm back. Sorry for the interruption there, but yeah, this is going to be flat. This doesn't describe it accurately because benzene, what they're saying here is there's a resonance structure for this. All the bonds are actually exactly the same. The resonance forms are just going to have the double bonds in the alternate positions. And so here was a single bond. Now we put a double bond there. And this was a double bond. Now there's going to be a single bond. So we just rearrange the bonds here. Where it's double and where it's single. And then we come up with this alternate structure here. And so these are two resonance forms. These are two ways of writing it. Now resonance forms, we don't move the atoms. So all the atoms stay fixed in position. The only thing we change is the location of the double bond. And so this is an alternate location for the double bonds here. The real structure is the hybrid. And so we have to make up the hybrid. The hybrid is going to be a mix, a 50-50 mix of both of these. And so in the hybrid, what we do is it's not a double, it's not a single, it's what we call a 1.5 bond. Or in other words, the double bonding electrons are spread out over the entire structure. And so it looks like this if we spread out and so all the bonds are exactly the same. Oops, like that in benzene. But that's the problem when you do benzene in this with Lewis structures and Vesper. If you did benzene with MO, what we call molecular orbital with full quantum mechanics, you know, for this, we get something that's already spread out. And so this is a benzene ring here. So this is the benzene ring, and you can see the alternating double, single, that. But when we do the, let's do this, let's replace that. It's flat, it's all trigonoplanar here, totally flat. But look at, do you see how the bonds are spread out now? All the bonds are exactly the same. Double bonding electrons have been spread out over the entire structure. So each bond is like a 1.5 bond here. We don't have to do that because, you know, we don't have to do this hybrid structure because, you know, it automatically does this in MO theory. In fact, if we look at the MOs for this, the MOs are already all spread out. Let's see if we can get one. maybe not that one. Find one. Yeah, like this. And so this is kind of the hybrid structure that we get. Everything's just evenly spread out. This is one molecular orbital here on benzene. The MO theory. In valence bond, I mean, in this type of thing, we do this. We come up with a resonance hybrid. The real structure should mimic the hybrid, not one of these resonance forms here. Okay, let me continue on here. Sodium formate, NaCHO2, you don't have to know the nomenclature of this, is the way an inorganic chemist is most likely to write the formula for sodium formate. Write the formula of the formate ion as an inorganic chemist is likely to write it. Now draw a Lewis diagram of the formate ion. Compare the diagram with formic acid. Is your formate diagram what you would expect from the ionization of formic acid? Let's just take a look at this. So formate, this hydrogen is non-acidic here. Formic acid has two hydrogens. One hydrogen is acidic. The acidic hydrogen goes on the most electronegative element, which is oxygen. So this hydrogen is acidic. This hydrogen is non-acidic. And so when formic acid loses a hydrogen, it loses the acidic hydrogen here, not the non-acidic hydrogen. And so we lose the acidic hydrogen, we're left with formate. And so we lose this as a proton. This bonding pair stays as a lone pair here. And this would be the structure of formate ion here. Draw two different Lewis diagrams. So this has isomers, you know, and so we could have different isomers. So they drew 4 of them. So pick any of the 2 that we come up with here. And so, you know, it could be 2 singles, it could be 4 singles, triple and a single. And so we play around with the bonding there to get it. C4H10O is the formula for diethyl ether, the same group. Okay, the same group of atoms is attached on either side of the oxygen. Draw the Lewis structure. So diethyl ether is very symmetric. They have the same group. And so this is what it looks like. An ether is a COC link. And so this is called an ethyl group here. So carbon with 3 hydrogens. This is a methyl. This is called methylene carbon here. CH3, CH2O, CH2, CH3. Compare, do something really quick. Compare Lewis diagrams for CCl4, SO4 2-, ClO4-, and PO4 3-. Identify 2 things that are alike about these diagrams and the way they are drawn from these generalizations. Can you predict the Lewis diagram of SeO4 and CI4? All right, let's just compare it. CCl4 is going to be, this is going to give us tetrahedral, EPG, tetrahedral Mg. That's it. This is sulfate here. Now sulfate, the way they drew it is they maintain the octet, but they kind of have high formal charges here. And so if we look at the formal charges, a little bit high, because all the oxygens are minus. That's going to make sulfur. Sulfur only has 4, but it normally has 6. So the sulfur is +2. It's a little bit high. And so this is how they draw it in Chem 4. But beyond Chem 4, you might draw it like this. We want to get rid of that formal charge. Can we expand the octet on sulfur? Yes. Sulfur we can expand. So if we make 2 double bonds, a double bond here on this oxygen, double bond here on this oxygen, we can drop the formal charge to 0. On sulfur and just have 2 negative formal charges on these oxygens here. And so let's take a look at sulfate here. So you'll see that most people are going to have 2 double bonds, 2 single bonds, and expand the octet. The reason they do that is to reduce the formal charge. Formal charge. The formal charge analysis here. These are formal charges. So for example, if they made no double bonds, we have a +2 formal charge. If we make 1 double bond, we drop it to +1. But if we make 2 double bonds, we drop it to 0 on sulfur. And then we reduce the formal charge on oxygen because these are now 0. So this is the structure that's most often shown for sulfate. Now, if we have two double bonds, we have a choice of positions. It could be top left, top right. You know, actually, it is tetrahedral, so it's a bit more complex. There are 6 positions that we can put the double bonds in. These are all resonance forms. The true structure is going to be a mix of all 6 of these, and it'll have the double bonds spread out over all the oxygens. And so the hybrid structure is going to have all the sulfur oxygen bonds exactly the same. And so the hybrid structure will have them all the same. They aren't doing the wedge and the dashes here, but they would be all the same. And so what we do is we'll just kind of dot it, smear it out all over these kind of thing. So you can see these are called resonance forms, and then we'll have a resonance hybrid. How many resonance forms is dictated by how many different combinations, you know? So this is, let's call this 1, you know, 2, 3, 4. It's a 1, 2 position. This would be a 1, 4 position. This would be a 2, 4 position. You know, how many different positions you have. It turns out there's 6 for this. Resonance forms, we have to be able to draw. I mean, something like sulfate with 6 resonance forms is kind of tricky to do. Here, there are no resonance forms. We have no double bonds. We aren't going to have a bunch of them. But you can see the advantage of this is all the bonds are equal. Well, in the hybrid, they're all equal. Perchlorate, we already did that one, you know, or perchloric acid. We did perchloric acid. This is perchlorate. We could put double bonds in there to reduce the formal charge. In this case, we'd probably put 3 double bonds in, you know, to reduce the formal charge to 0. So if we look at perchlorate ion, you can see they'll put 3 double bonds here to reduce the formal charge. But the hybrid, you know, it's how many different resonance forms could we draw for this? And so let's take a look at that here. Hopefully somebody did that for me so I don't have to draw them all out. How many resonance forms? We don't have to do the 3D structure for the resonance forms. No, nobody did it, so I guess I'll have to do it. How many resonance forms can we do? Okay, here's 1. Okay, that's top, left, bottom. Here's 2, left, right, bottom. Here's 3, left, top, right. How many more are there? Well, this is the same. You see left, top, right, that's the same. And so let's see, I think there's still only 1 more. And the 1 more structure that's not shown here. So as far as resonance forms go, how many different variations? We have to leave the atoms fixed. So that's 1, that's 2. We show these with a double-headed arrow. And this would be 3. And the 4th one is going to look like this. It's going to be top, right, bottom. And on the left, we'll have a single. And so this would be the 4th here. And then we, of course, we put in all the lone pairs here and the formal charges and the net charge, you know. And so we get a total of 4. And then the hybrid structure would have, you know, the double bonds dotted over all 4 bonds like this. That would be the hybrid structure here. And it would be 4 different combinations that we could get for perchlorate. Phosphate does have a formal charge, and that formal charge can be reduced by expanding the octet by 1. So if we make 1 double bond here, then that'll reduce that, like I talked about already, I think. And so for phosphate, typically you're going to see 1 double bond there, you know, when we look at phosphate online. That 1 double bond is to reduce the formal charge, you know, down to 0. The formal charges for phosphate. course, we want to calculate all the formal charges. Choose the best Lewis structure for phosphate. Well, how many resonance forms are there? Well, we can count them. Here, bottom is 1, left, that's 2, top is 3, and right is 4. There are 4. So we could have the double bond on the bottom, the left, the top, or the right. And so we got 4 resonance forms for this. Now, this is not good here because, you know, we make 1 double bond, that's good because that's going to lower the formal charge to 0 on phosphorus. But if we make 2 double bonds, then we go negative. So there's no advantage doing this because now the formal charges are getting worse. You know, here. And so that's why we stop here. What's going on here? Yeah, again, they made 2 double bonds. No. Here, there's no double bonds. No double bonds, the formal charges. This is, your book is going to leave it like this. You know, this is not conventional. Let's ignore that. Showing. These are polyphosphates. No, on the polyphosphates, do you see they all have double bonds? And so if we look at the structure of something like ADP or ATP, let's look at ATP. And look at the structure for ATP, they all have double bonds to reduce the formal charge. And so when we look at ATP, you're going to see expanded octets with double bonds here to reduce the formal charge. And so this is the standard way it's written, except they're missing all the lone pairs, which is too bad. They really should put the lone pairs on there, especially for beginner chemists. The beginner chemists should, it would be better. Okay. Here's 3D structure. These are tetrahedral. These are tetrahedral with a double bond there. So the double bond is going to compress this angle here and widen this angle here because double bonds take up more space than single bonds. So this would be ATP. I wonder if we can get the angles for those here. Well, we could, I could do that. It'll take me too much time to make it. I think so. I'll just leave it off from there. It's phosphate. It's the same thing with selenium. Selenium is going to have a +2, so we could form 2 double bonds there, like sulfate. It'd be the exact same thing as sulfate, 2 double bonds. CI4 doesn't need any. You know, carbon already has an octet. All the formal charges are 0. So CI4 is like CCl4. All these are tetrahedral. Tetrahedral EPG and tetrahedral MG. All the angles are 109.5. 1,2 dibromomethane, the shapes. Well, draw out the Lewis structure. It's trigonal planar. C2, there's a double bond there. It's a carbon-carbon double bond. When we try to draw out this using just our regular way, like carbon-carbon, we'll make that, and then we have 2 hydrogens, so maybe we'll put a hydrogen here and a hydrogen here, and then we have 2 bromines like this. We'll put 2 bromines, and then we'll complete the octets on the bromines. There are no formal charges, and then the carbons are short, and so we'll have to do double and 2 singles like that. And so it comes out like this, trigonal planar. Acetylene, we already did that. It has a triple bond, a single and a triple. And butane's all tetrahedral on the chain, zigzag chain of tetrahedral. Okay, let's try something with resonance and hybrid and that kind of stuff. Let's do this. Let's see, what time is it? Okay. We're going to do, I want you to do this. Let me see, on chapter 13, I didn't do chapter 12, did I? Yeah, I guess I already went through chapter 12. Can you do the Lewis structure of bicarbonate? When people say shape, they're talking about the molecular geometry, not the EPG, but the MG. All right, we're gonna make this into a quiz here. So we'll do breakout rooms for this one. If you have requests, let me know. Okay. All right, so work on this. Let me know if you need help.